Hi everyone, I hope you're all doing well. It's a bit of a change of scenery for me. I'm in Japan, which I'm super excited about. I absolutely love it here. So excuse the slightly different backdrop around me. Erik, as ever, is still in the Netherlands. Erik never moves. You always have that beautiful, studious backdrop of books, Erik. But yeah, it's been a really busy October for us. We've just launched a really exciting new set of features around community solutions, a really big update to how they work. We now deduplicate solutions. So if lots of people have submitted a similar solution, you only see one version of it. We've also added some new ordering options. So you can sort by things like fewest lines of code, the most highest reputation user to have submitted a solution, the highest frequently submitted solution, various options, go and explore them. You can also now search by code, which is really exciting. So you can go and search for anything you're interested in finding in people's solutions. And if you have a look at C#, and it's just C# at the moment, you'll see that we're also now allowing you to filter by programming concepts. And those can be things, constructs in the languages, like whether a solution's used an if statement or a switch statement. But they can also be deeper things like, have they used recursion? Are they using bit shifting? Are they using higher order functions? So we've just done this so far in C#. It's been a lot of work in the background to do that for C#. But now we're trying to build an intelligent neural network that we can use across all languages that does the same sort of thing. So there's lots of active development going on there. We're really excited about it. It's looking really good and like things are going to go well there. But yeah, do go check out Community Solutions, check them out in all the languages, but have a specific look on C# as well, and look at some of the details there. And Erik, I know you've had a lot of fun building some of that. It's been a really enjoyable project so far. But anyway, we're here for 12 and 23. So in October, we looked at languages that were object orientated. It was object orientated October. It was really interesting. It was really fun. But for this month, we're taking things a step more to the wild side. And we're looking at assembly-based languages. And we're going to talk a little bit in this video about what assembly-based languages are. If you're not used to assembly, we'll explain a little bit of the fundamentals. And then we're going to look at 3 specific languages. We're going to be looking at MIPS assembly, we're going to be looking at x86 assembly, and we're going to be looking at WebAssembly, which is, if you're involved in web development at all, is something that might be coming across your radar. So Erik's going to be doing most of the talking, as he normally does, and enlightening us with his wisdom. But before we start, just a reminder that there's a badge you can earn for this month, and I don't think I've said yet, we're calling this month Nibbly November. We'll come to that in a second. And you can get the badge by completing any 5 exercises in any of those 3 languages I just mentioned. But there's also 5 specific exercises that are part of the year-long badge that I know many of you are collecting for 12 and 23. And there are those 5 featured exercises you can complete in any of the 3 languages, but you have to complete 5 exercises. The first is pop count, where you count the number of bits in a number. The second is grains, where you calculate the number of grains on a chessboard with some doubling squares going on. Resistor color, been a big exercism exercise for a while, where you convert a resistor's band's colors to their numerical representations. We also have rotation cipher, where you implement a rotational cipher, and in particular the Caesar cipher. And then finally, we have nucleotide. How do I say that, Erik? Nucleotide count, where you compute how many nucleotides occur in a DNA string. So those are the 5 exercises if you do want to complete the year-long badge. So Erik, first question to you. I just mentioned this is Nibbly November. Why did we call it Nibbly November?
Well, as you probably already know, 8 bits are called a byte, and a nibble is a bit smaller. It's 4 bits. And so the name starts to make sense if you think that, hey, a byte, if I swap the Y with an I, you get a byte, as in taking a bite of an apple. And a nibble is then a small byte.
Excellent. That's incredibly nerdy and geeky. I love that. So, okay, so nibbles, because we're dealing with bits and bytes. So let's dig in a little bit to what that means. Do you want to start off just by explaining what an assembly language is, just giving us a bit of a brief overview to the whole idea of assembly languages, Erik?
Yeah, sure. Let's start with some basics. A CPU, or central processing unit, executes instructions. And these instructions can be like add two numbers, shift bits to the left, etc. So very low-level things. These instructions are known as machine code instructions, and they're in essence nothing more than specific sequences of bits. So you could consider the instruction to add two numbers to be 00001 or whatever, and then subtraction will be 0101 or whatever. There's a unique sequence for each instruction. That's the key thing to remember. And then executing a full program, which is also a sequence of bits and bytes, of course, is simply, in quotes, of course, the CPU processing those sequences and then translating them, interpreting them as instructions, and then executing those. So, in essence, the CPU has a set of machine code instructions built into them, and a program has the codes for those instructions in them, so the CPU knows what to do. So that's the bare basics. You can imagine that directly writing these sequences of bits is quite cumbersome and error prone. So in 1947, Kathleen and Andrew Donald Booth came up with a more human-friendly language to represent machine code instructions in, well, a more friendly way, one that is easier to remember, easier to write. And such a language that represents machine code instructions, but it's in a different format, is called an assembly language. And this assembly language is then converted into actual machine code instructions via an assembler. So you can see this is the basic setup for an assembly language, where you're not writing the zeros and ones yourself, you're writing them in a human understandable format. So you would have an add instruction, and you would write add, add, as in the word, instead of that specific combination of bits. One of the interesting aspects of assembly languages, which is very different to other languages, is that they're usually directly tied to a CPU architecture. So if you have an ARM CPU, you must use ARM machine code instruction. You can't use x86 instructions. And if anybody has a newer MacBook, you'll figure this out very soon, because you need to enable some settings to do like an emulation layer. But it is a result of the fact that you're trying to maybe use x86 code on an ARM machine, and those are incompatible machine code instructions. So this is something to keep in mind, that the machine code instructions are always tied to a specific CPU architecture. They are usually operating system independent, so it doesn't matter if you run Linux or Windows on your CPU, but it does matter what the CPU's architecture is. And for those of you old enough to remember punch cards, those big cards with all the holes in it, those were essentially assembly language too. They were instructions, and they were encoding the machine code instructions, but in a higher level format. So it was at least better than machine code instructions, but it was still quite unwieldy. But they were assembly language.
I wonder if we should try and create a punch card language on Xism, where you actually have like a GUI where you can punch the holes in the punch cards. And I feel like that would be the ultimate step on our journey to represent every language, is going right back to the beginning. It always amazes me how many ideas and concepts and things came out in the late 1940s. Like so many of even just the first set of thinking about AI was back in the late 1940s. Like so much of the foundation of everything happened in that short period of time. From a programming historian perspective in me, I find it fascinating how much intellectual vibrancy there was at that time. So how does, I mean, you sort of touched on it a little bit, but how does like programming in assembly language differ from programming in the languages we're more used to now?
Well, it's probably obvious by now that the key difference is that assembly language are very low level. You can't get any more low level except for writing the bits out yourself. But you'll be basically missing a lot of the abstractions that our current languages provide you with. So, want to have classes or objects, they're nowhere to be found. If you want to have a for loop or a while loop, tough luck because you have to write them manually via jumps. Functions, nah, not really. I found it very humbling when you start out writing assembly language because you just realize there's so much there that I have to write myself that all the language that we use provide us with by default. So you don't have to really realize how much there is going on just to have a for loop or a while loop. And those are even the simpler concepts. So I'm not even talking about classes or strings or whatever. There is so much that a modern language helps you with, and there's a lot of that going on under the hood that we don't even think about it, but it is there when it gets executed. So it's very humbling. And I would argue that it's also incredibly useful to write assembly code, even though it can be very hard. But you'll definitely gain a better understanding of how things work internally, and you come to appreciate what our languages do. So I think doing assembly code will make you a better programmer, and in very rare cases, actually applicable to your job. But that might be very, very rare case indeed. Just as a random fun fact that I found while researching this is that I don't know if any of you ever played Roller Coaster Tycoon, which is like a roller coaster simulator game. But 99% of the source code of Roller Coaster Tycoon was handwritten assembly code by a single person. It's actually one of the greatest achievements in gaming history, I feel personally. So if you've never done assembly programming, you're now starting to do it a bit for this Nibbly November, you really will appreciate how much effort went into that, how much of an amazing feat that was.
I do wonder when you say that whether the reason it's 99% is because it takes about 50% of the game just to write one for loop. It'd be really interesting to know which bits of Roller Coaster Tycoon were done with that. I presume a lot of the mathsy stuff. The volume of code that took up as a result.
Well, he has to do graphics too, that person. So graphics are
I guess it's the
whole other
ball
game.
Yeah,
just writing a for loop is still relatively easy.
Yeah. And for everyone watching this, so Erik talked a little bit there about how humbling it is to write assembly code. I'd just like to point out that, Erik, you told me that you solved, I can't remember which exercise it was, but tried solving an exercise, and it was, I think, like the first time in like 15 years or something you'd written assembly, and you managed to get it perfect first time.
Yeah, that was really exciting.
However humbling it is for you, Erik, you still were perfect at it. So it can't humble you that much. It must have made you quite proud at the same time.
It was just one exercise, but I really, because it's sort of different the way in that you solve these things, because you have to, it's more all or nothing than other language, I feel, because it's so easy to make mistakes. And then you get somewhat harder to parse errors often. But I think it was I don't even know which exercise it was, but it was in MIPS assembly. And when it worked, it was just like, wow, I almost felt like I really control the machine or something like that. It's like, I can't get any lower. I'm the puppet master or something like that.
Yeah. Yeah, you feel you have infinite power, but you also know that to do anything substantial would take you a lifetime.
Yeah.
So, I mean, away from Roller Coaster Tycoon, are many people actually writing assembly code anymore? Is this like a modern art, or is it a dead art, or somewhere in between?
I guess somewhere in between. It's definitely less than what people used to, of course, because we have so many other languages now. It used to be the case, maybe a couple of decades ago even, that handcrafted assembly was still outperforming a lot of the compiler-generated machine code. And this is also one of the reasons why C++, for example, allows you to embed WASM, so inline assembly code, in your C++ source code. So the idea being that for some parts of your source code, you might want extreme control over what's happening, and then you would just handwrite your assembly yourself, which I had to do in high school. That was quite fun. But nowadays, it's often a futile effort to try to beat the machine code that our compilers generate. So I wouldn't necessarily think that you get far trying to do that. But in very, very, very specific use cases, for example, incredibly performance critical or resource constrained environments, it might still actually be useful to write handcrafted assembly. But it is sort of an art almost, in that you don't really, it's often not taught anymore in universities, because it's becoming less and less important over time. But people are still using it, and it's of course a great way to still understand what is happening under the hood.
Mm-hmm. Cool. So, shall we dig into the languages?
Sure.
I think we should go chronologically. So, first released, we're looking again, just a reminder, at MIPS, x86, and WebAssembly. So, should we start with MIPS?
Yeah, sure. So MIPS is an acronym of microprocessor without interlocked pipeline stages, which you can forget immediately. But the thing that you have to remember, it's a family of what's called reduced instruction set computers. So there's RISC, RISC. You might have seen that occasionally somewhere on the internet. So RISCs are architectures where the instruction sets are actually quite compact. So it doesn't have that many instructions, and that has a lot of benefits. But we'll come to those later on. MIPS was developed by MIPS Computer Systems, that's the name, and was first released in 1985. There have been multiple versions of MIPS, MIPS 1 to 5, and then followed by MIPS 32-64. So the first two versions were 32-bit only, but with MIPS 3, 64-bit support was added. And every single version after that supports 64-bit too. Mm-hmm. There are several optional extensions to the instruction set. So those are additional instructions for specific purposes. So you might have heard of SIMD, SIMD, which are instructions to do vectorized operations. So we'll come to that later on, but it means that you can do a lot with just a single instruction. There is an extension for compression, so that there's less binary data to transfer. But the idea is that you can get you have the basic instruction set, but if your specific implementation of MIPS needs to run SIMD for performance reasons, for example, you can add that. MIPS is very influential to later RISC architectures. So a lot of them took inspiration from how MIPS was designed. But MIPS itself, it was announced in 2021 that the MIPS architecture was no longer being actively developed, and that they were migrating to RISC-V. And the interesting thing about RISC-V, and this is very unusual for a processor architecture, is that it's an open source royalty-free architecture. Especially the royalty-free bit is quite unusual. So MIPS still exists, but it isn't actively being developed anymore. MIPS is mostly used in embedded systems like routers, but also in servers. So if you remember the early days of graphical effects in movies, like Jurassic Park or whatever, a lot of those special effects were being generated on silicon graphics computers, and they were using the MIPS instruction set. And the NEC Senju 4 supercomputer, one of the earlier supercomputers, also used MIPS. Tesla's Model S actually uses MIPS. NASA's New Horizon probe uses MIPS. And so those are all relatively recent projects. And you can see that even though it's not actively being developed, it's still being used. And then, of course, it's being taught in universities all over the world. And one final thing is that it has been extensively used in gaming consoles. So the original PlayStation, PlayStation 2, PlayStation Portable, and the Nintendo 64 all use MIPS as their CPU instruction architecture.
Very interesting. Okay, and then on to x86-64, which is probably the version of assembly that most people would be familiar with. It's what I think of when I think of assembly.
Yeah, I think so. That's indeed the case. x86-64 was designed by AMD, was released in 1999 under the name AMD 64 architecture. As you probably can guess from the name, it's a 64-bit version of the x86 instruction set. And that x86 instruction set goes back a long time. So that was introduced in 1978 by Intel when it launched its 8086 microprocessor, which was itself a 16-bit processor. But then you got the 286 and then the 386. So the 8386, the numbering is quite crazy, but it added 32-bit instructions. So it became a 32-bit instruction set. And whenever you're saying just x86 without the 64, it's basically synonymous with the version that was introduced with the 803086. So why have a 64-bit version at all? Well, it's mostly for being able to address more memory. So if you are addressing memory, which you do in your assembly code, you're saying, hey, give me the integer that is at this memory position, you use an address for that bit of memory. But with 32 bits, the maximum amount of memory that you can address is 4 gigabytes. And that used to not be a real issue in the beginning of the 80s. But when we got more and more memory, this started to become a bottleneck. But with 64-bit, you can, in theory, address 16 exabytes. Although it's interesting that the x86-64 assembly only uses 48 bits, but that still allows 256 terabytes of memory to be addressed. So I think we're good for now. But if we ever need to go to the exabytes bit, we can just use the other 16 bits too. But that was the key reason why 64 bits was a big thing. But it was not only that. So AMD 64 extends the x86 instruction set, but it was still, because it's just an extension, it's still fully compatible with existing 16 and 32-bit applications. So your machine at home, if you're running an x86-64 CPU, which is very likely, you'll still be able to run 16 and 32-bit applications, which is quite crazy, actually. They have a compatibility mode and it still all works. And the reason why, well, everybody thinks of Intel as the market leader for long, has thought of Intel as the market leader. Intel had actually done a project together with, I think, Hewlett Packard for another instruction set. It's called the IA64, another 64-bit instruction set. But AMD was not involved. And it was a very new, very different, backwards incompatible instruction set. But that proved to be its downfall, because AMD 64 was backwards compatible. So all the existing software would still work. And in the end, Intel had to admit that AMD's approach was better, or at least that was what the market wanted. And they implemented their own version of it with only some minor semantic differences. So if we're talking about x86-64, it was actually designed by AMD and later on implemented by Intel. Although their press releases always make it sound like it's the other way around, but it's really not. It's AMD. So where is it used? Well, this is very simple. It's used everywhere. So it's like all the workstations in the world, there's just a small percentage that is not using x86-64 assembly. Many servers, including supercomputers, embedded systems, but also gaming consoles. So, for example, the latest iterations, so PlayStation 5, Xbox Series X, they use x86-64 CPU, and it's all over the world. There's basically no place where you don't get x86-64 assembly being run.
Nice, very interesting. You mentioned about how it can address, did you say 16 exabytes? One of my... well, the only time I've ever come across exabytes anywhere in the real world is if you mount Amazon's Elastic file system onto your one of your Amazon servers. So this is like a file system that I guess is basically like the size of the whole of Amazon storage, like S3 or something, and then you just run like df in Linux, so disk free, to tell you how much space is used, it always comes up and says there's 8 exabytes of free space left on that hard drive, which always makes me chuckle a little bit. But I think that's probably like just a fixed number as well. I doubt there's any relevance to the real size. It's probably just how much the biggest number Linux can comprehend as something that could possibly be there. Cool. So on to the third one. This is, I guess, the new kid on the block, but also the one that's probably getting the most innovation and development around it right now, and that's WebAssembly.
Yeah, so WebAssembly was designed by the W3C, the standards body for web technologies. It has a specific set of design goals. So it wants to be fast, safe, and portable, and it also wants to be efficient and portable. So the semantics are the first one, so fast, safe, and portable semantics. And the second one is the implementation has to be efficient and portable. And back in the days when we were doing web, if you wanted to have things run really fast, so for example, games, you usually did that via specialized browser plugins. So you probably know Flash. Flash was famous for being flashy, so you could build games with it and it would still perform very well. But it did require you to install the Flash plugin into your browser. Same story applies to Silverlight, which was a Microsoft technology, another browser plugin. That was ActiveX. There were Java applets. And there were a ton of these plugins that did something to improve the speed of your code over JavaScript. And JavaScript was built in. So why did they do that? Well, JavaScript, the language, has some features that don't lend itself very well to being optimized, even though there has been a ton of work going on there, and JavaScript performance is tons better than what it was 20 years ago. But still, it was hard to get it to up to speed, and especially in the beginning of the web days, Flash was king. But there were also downsides to using these plugins because they usually came with security concerns, and you'll remember that you had to update Flash because otherwise there will be very major security concerns. Same went with Silverlight. They were not standardized, so Flash was just Adobe, and Adobe controlled Flash. And that was not ideal. And one of the efforts that, famously, the iPhone stopped supporting Flash, which was like the death stroke for Flash. But other companies took this upon themselves to try and figure this out. How can we get things to run efficiently in the browser? And what Mozilla did was they designed WASM.js. So WASM is a shorthand for assembly. And it is a subset of JavaScript. So it doesn't allow for all things that you can express in JavaScript, but a subset. It's still JavaScript, but there are some things that you can't use. And this subset was specifically chosen to allow for running the code in the browser with great performance characteristics relatively to standard JavaScript. So the main reasons why WASM.js code was performing well was because it had type consistency. So if you might remember from a previous introduction, JavaScript is dynamic. So types can change. It can be a Boolean 1 minute and then a number next, and then the next time it can be a string. And that is very, very hard for your browser to optimize. So the runtime has to account for that. It has to constantly check whether or not the type has changed. But WASM.js achieved a type consistency. So if it was an integer one time, it will be an integer all the times. And this allowed great optimizations to being applied. And the second thing that they did was no garbage collection. So garbage collection is infamous for being bad for performance, even though it's good for writing code. So languages could compile to WASM.js. So C, C++ could compile to WASM.js, and then you get good performance in your browser. So the idea was that WASM.js was a compile target. So you wouldn't be manually writing WASM.js because you could, but you would normally use a compiler. But it was still JavaScript, so it was limited in what could be achieved. And then all the big companies got together and they came up with the idea of introducing something new, something that would be, well, what I mentioned before, fast, safe, and portable, but also efficient. And that became WebAssembly, or in short, WASM. It's an WebAssembly, so it's an assembly-like language, but it is slightly different from the other language that we've just mentioned. The main difference is that WebAssembly is not tied to a specific CPU architecture. And remember that I said it had to be portable, and it also has to be portable across CPU architectures. So WebAssembly does not compile to machine code. It's actually bytecode, an intermediate representation, although still a very low level one. So it sort of, if you squint a little bit, it looks like assembly code, but it's not actually compiled to machine code. It's an intermediate binary format that is then interpreted or evaluated in a runtime. So there's a runtime in every single browser, major browser now. But so it's platform agnostic. It doesn't compile to machine code. So the downside of that is that of course, every platform has to have a virtual machine, but we've had many vendors building those, so that's hardly a problem anymore. It is a statically typed language, so it's a crucial difference from JavaScript. And this static typing, as I mentioned before, the fact that you know what a type is allows for great optimizations in the runtime. It uses ahead of time or just-in-time compilation. So you usually pre-compile things or have it pre-compiled when you need it, although it could also be interpreted. You could even write that yourselves. It's an open standard because it was developed by the W3C, which is standards body, and it consists of two parts. So the most important one is the binary format, and that defines all the instructions, the semantics around these instructions. But there's also a text format, which is just a human-friendly way. So you remember the machine code versus assembly code bits? So you could see that the binary format is the machine code bits, although it's not actual machine code, and the text format is assembly language. So it's a more human-friendly format, which is then compiled to the binary format. So what gets executed is the binary format, but you can also define it in text format and then compile it to the binary format. I've mentioned before that all major browsers have support WebAssembly, so they have built a runtime into their browsers, and this is used in basically web pages that require high performance. So great examples are Google Earth, Figma, Unity, and AutoCAD. And it has also been gaining traction on server side, so not in the browser, but on the server. For example, to run microservice services, to run on software as a service platforms, for example, Cloudflare workers, or even in Docker.
Very cool. And then thinking of these from a programming perspective, if you're working with them, how does it differ to work with them? How are their, I guess, architectures different when you're working from a programming perspective?
Yeah, so MIPS assembly uses what's called a load store architecture. It's also known as a register architecture. And if you're not familiar with registers, you can see them as sort of these predefined memory locations where you can write things to and you can read things from. And those are called registers. You have a fixed amount of them, so you have to be clever in how you handle those. But that's where data is being stored, apart from a memory, of course. But if you do operations in MIPS, you have to load a bit of data from memory into a register, or you just put something in it, not necessarily from memory. And then the instructions have to work on a purely register to register basis. So the input is in registers, can be more than one, and the output is be in one or more registers too. So if this doesn't make sense to you, it will when you start working with MIPS, because if you think of defining a variable or something like that, that basically means storing data in a register or a bit of memory, but in the end, you have to put it in the register to actually work with it. And that's different from x86-64 assembly, which uses a register memory architecture. And this means that you can have instructions that work with partly with the register and partly with memory. So you don't necessarily, if you have something in memory, you don't have to copy it to a register for the instructions to work, but you can have it work directly on memory too. So that's a bit of a difference. And then finally, WebAssembly is quite different because it uses a stack-based programming paradigm. So it's not register-based, but it's stack-based. So you push and pop things from the stack. So adding two numbers means pushing a number on the stack, pushing a number on the stack, then pushing the instructions to add them on the stack. That will be recognized. The instruction is popped, the two operands are popped, and what gets returned, pushed back onto the stack, is the result of the addition. But you do have options to read data from and to memory. But the way that you work with the stack is quite different from MIPS and x86, which are much more register and memory based.
Really interesting. So they're actually really quite different to work with then, despite being three languages in the same family. They'll feel very different to work with. And so if someone's choosing which of these languages to do, what is it that makes them great? Why would people take an interest in them? Again, maybe starting with MIPS.
So MIPS is very small. So the instruction set can fit almost on a single page. And of course, that's the reduced instruction set bit of RISC. But it is a great feature of MIPS because it makes it easier to learn. There's just a limited amount of instructions that you need. Especially if you compare that to something like x86-64, which has tons of instructions. Furthermore, MIPS has very established calling conventions. x86 has them too. But this helps you to basically identify where do I put data, where do I get my data, where do I need to store data to return things. And it's basically guidance on how you should be using your registers. And it can be very helpful when you're just starting out with MIPS. It's also a very stable language, and it will be very stable because it's no longer actively developed. And the last version was released in 2014, so it's already almost 10 years. And this also means that if you know MIPS from 10 years ago, you know MIPS now. So it's basically the same thing, and that can be incredibly useful. MIPS is widely documented because of its age too, but also because of a lot of academic texts have been writing about MIPS. And another great thing is that MIPS has lots of real-world usage. I've listed a ton of the existing examples, like the PlayStation and the Mars and the NASA exploratory vehicle. So it's used on billions of devices. So if you know MIPS, there's a huge market of things that it can run on. Moving
nice.
on to
sorry. Yeah. No, I was just going to say I like the idea that it's stable because no one develops it anymore. I think that's as good a definition of stable as we're going to get. Yeah, x86-64.
So whilst x86 assembly is an extension of x86, it does add a lot of new features. And most notably, apart from the addressing bit where you can address more memory, 64-bit integers are also added. So you can have numbers with a greater range without having to split them into 32-bit numbers. You can work on them as a whole. There are additional registers for you to work with, so you have more room almost to work with. You get SSE instructions, which are vectorized instructions. I mentioned before that just think of these as very efficient. And you get relative data access, and we don't need to go into that, but it's basically a feature that makes when you're using shared libraries, which you often are, so it makes them more efficient when being executed. And then one other interesting thing is it introduced the no execute bit. So you have if you have memory, it's often divided into pages. So you just think of that as a bit of memory. But you can set the no execute bit on specific pages, and it means that you can't run any code, so you can't have any executable code. And this is a security feature because you know of some bits of memory that should be there just for reading, and you won't ever execute anything, or maybe. And then you can set the no execute bit, and this is bad news for hackers basically because you have one less thing that you can use. So security was also a concern. Another great feature of x86-64 is that it is very it's familiar. It's an extension of the x86 instruction set, which many people had already had experience with. So for all those people that have already worked with x86, the 64-bit extension will be relatively easy to learn because it's so similar and it has all the instructions that you already know in it. It has been around a lot, x86-64 assembly, and as it's so widely used, the documentation is basically as extensive as you can get. So extensive documentation, detailed, tons of resources to find. This makes it a really good language to work with just because of the huge amount of resources that you can use to learn the language and to troubleshoot, which is often necessary when doing assembly language, at least for me. And then finally, a great feature is that it's very stable, like MIPS, although it's still being developed. So new versions are added regularly-ish, but the core remains the same. So I mentioned that 16-bit and 32-bit are still being supported, and that goes to show that it's a very stable instruction set with instructions just being rarely updated. So you can still use old instructions that you've been using for 20, 30 years or so.
Interesting. And finally, then, WebAssembly. What makes it interesting? What makes it great? What makes it worth learning?
So WebAssembly has the stack-based virtual machine, and it's actually quite lean and simple compared to other assembly languages, including RISC. That is, the execution model is just, it's easy to visualize, and it's relatively easy to implement because you're just implementing a stack-based virtual machine. And if you've ever worked on a virtual machine, and maybe you have ambitions, a stack-based virtual machine is actually quite easy because you just have the stack to work with. But it also makes it easy to compile for because stack-based operations are well known. It's easier for a lot of things. But this core of being a stack-based language, stack-based instruction set, it makes it very easy and lean. Another great thing is that WebAssembly, the text format uses S expressions. And if you remember in June, we had a month where we looked at Lisps, and Lisps all use S expressions. So the whole parentheses bit, those are S expressions. So if you've ever worked with a Lisp, you'll immediately be recognizing that WebAssembly text is written in S expressions. And this allows a certain sugar, so it's like syntactic sugar, where you can write things in a way that looks quite imperative, but under the hood it will be translated to just imperative stack-based operations. So you could, doing an addition of two numbers, you could write something like between parentheses i32.add, and then you do constant 1, constant 2, and that will actually be translated to push this thing, push the constant 1 on the stack, push the constant 2 on the stack, and then do the addition. So it reads very pleasantly, especially compared to those other two machine assembly languages, which are more hardcore, I say. It's slightly higher level than the other two. Another great feature is that it has strong interop with JavaScript. So, of course, it runs primarily in the web. It's not exclusive, but we'll get to that. So you need to have data being passed in and out of WebAssembly for it to be really useful. And this is very important because if you do WebAssembly, you can't interact with the document object model, the DOM. So you can't create nodes or read them or whatever. That all has to happen in JavaScript, and then you have to pass things into WebAssembly. So you don't get to work with the DOM directly in WebAssembly yet. You never know, but it's not there yet. WebAssembly is also a very new technology, and it's still being improved a lot. So we're still at I'm not saying it's the beginning. We're sort of past that initial phase, but there's still a ton of things that they want to add to the language that haven't yet been done so. So the virtual machines are, of course, being improved all the time, getting more performance, etc. But the standard itself, there are proposals for SIMD instructions, garbage collection, threads, tail call optimization, and much more. It's all open because it's W3C, of course. But just this goes to show that the language is still and the instruction set is actively being developed, and there will be cool new stuff being added later on. It's also a very safe language, and that's quite a unique feature of an assembly language, which usually does not pair well with safety. The code of WebAssembly is validated beforehand when it is compiled, and it is run in a sandbox environment. And this is really important because in a sandbox environment, it's really, really hard to influence other running code. So you get a high degree of security compared to JavaScript or native assembly languages. The semantics of WebAssembly are also very well defined, making them easy to check either manually or automatically, and also easy to reason about.
Really interesting. And so continuing to look at these from a programming perspective, do any of them have any standout features that would make you interested in learning them?
Yeah, so MIPS, I think one of the standout features is efficiency. So there's a reason why MIPS processors have been very successful and have been used in a wide variety of use cases. And part of the reason is that they're very efficient. So low power usage, etc. So that makes them great for embedded systems, which is why you see them being used in things like routers, etc. So the efficiency of MIPS is absolutely one of its standout features. And a second feature, a standard feature, is performance. So efficiency paired with comfort performance. And that's actually, well, of course, a brilliant combination. So MIPS has been used in supercomputers, but in general, MIPS has great performance. And this is also partly due to its reduced instruction set, because it makes it easier to anticipate what can be done. And it's easier to build something that interprets those instructions. But in general, MIPS has very good performance. And that's one of its strengths. And then a third standard feature is that it's easy to learn. I mentioned that the instructions could fit on a single piece of paper. There's also the thing that the instructions themselves are relatively straightforward. So they usually do just one simple thing, and that makes it easy to learn. So it doesn't have a lot of then this and then this and then that habits. It's just copy one thing from this memory to that bit, etc. So the instruction set that itself is concise, and it's also very well defined and relatively simple. So great for teaching. And that's, of course, one of the primary reasons why MIPS is used to teach assembly in many university classes. And then we have x86-64 assembly. And the primary standout feature is its performance is powerful. It has been tweaked over decades with tons of instructions being added that help with performance. A great example is SIMD, single instruction, multiple data. So you have so consider that you have an array of integers and you want to, add one to them. Then you might have an instruction that says, hey, add one to all these bits of data in the same time instead of going over them one by one. So it's a form of parallelization. And SIMD has a lot of benefits, especially when you're doing more complex things. So, but there are more other extensions to x86-64 to other instructions that can help greatly with performance. And also that's why, of course, a PS5 and an Xbox Series X, which are gaming consoles, which are often aiming to squeeze out every bit of performance out of them, they use x86-64. So that says enough, I think. It's also ubiquitous. So you see x86-64 everywhere. I mentioned some examples before. Intel AMD CPUs implemented, and they are also everywhere. It has actually been the de facto standard of assembly languages. So if you work with assembly, it's a very reasonable assumption to make that you're working with x86-64 in the majority of cases. And if you want to learn an assembly language that just runs everywhere, it is everywhere, then you learn x86-64 assembly. The language is also regularly updated. So I mentioned the SIMD instructions. There's a whole suite of vector instructions. So you have SSE, but also SSD 325, AVX, AVX512. We don't need to go into the details, but it's suffice to say that the new instructions are added regularly, and it's usually just for performance or enabling features that might not have worked in the past, but that are very important now. So parallelization was less important a while back, but it's becoming more and more important because of Moore's law not holding up anymore.
Mm-hmm.
And then finally we have oh, sorry, you were saying?
Yeah, I was saying finally WebAssembly. I just talked over you. Sorry, Erik.
Yeah, finally WebAssembly. So one of the standard features is its efficiency. So the binary format is quite compact, and it can be decoded, validated, and compiled in a single pass. So that's always great. But another great thing about the binary format is that it's streamable. So if you compared it to JavaScript, with JavaScript, if you have a very large JavaScript file, you first have to get the entire file, then the entire file is parsed, and then it can get interpreted. But with WebAssembly, while you get data streaming, you can already start interpreting it. So you can compile it, you can validate it, you can decode it, but it can all be done without having seen all the data. So this makes for a very efficient way, especially if you combine that with later HTTP servers that allow for the streaming bits to be very efficient. And it's also parallelizable, so you can run things in parallel. And that's also a specific design option that they built into it. And this makes it perfect for high-performance web applications. There is less to send, it's easier to run and quicker to run, and it's just in general very efficient. That's what they set out to do. WebAssembly is also a great compilation target. So the other assembly languages too, you usually don't write the assembly yourself, but you compile to machine code via a compiler. But with WebAssembly, that's actually one of the goals. One of the goals is that you write code in a different language, and then you compile to WebAssembly. And that will allow you, that compiled WebAssembly can then run in the browser. And this enables a lot of languages to basically get running in the browser for free. So they don't have to, build a JavaScript framework or whatever. They can compile to WebAssembly, and then that WebAssembly can run in the browser. And there are actually two different ways in which languages can do this. Most of the languages will just compile your code to WebAssembly. But you also have a different option. So a Java or a .NET /C# will compile to bytecode. And what they do, at least I know from the C# bits, is that they compile the runtime to WebAssembly. And that runtime can then just interpret your bytecode unchanged. So that's actually a different way of looking at it. So it's just you produce the same bytecode, but then it gets interpreted in the browser because the runtime has been compiled to WebAssembly. And this blows your mind once you see it, but it goes to show that everything will eventually be able to run in the browser via WebAssembly, except for very niche and unusual things. Another standard feature is that it's easy to deploy and run, so the binary format is small. You just need a virtual machine that can interpret the bytecode, and it's portable, so all the browsers included, but it's also being used more and more outside of the web space, so on servers, etc. And you can use it in many places. And that ties into the last standard feature, that it's not tied to the web, but also it can run server-side. So there's actually nothing much that prevents you from running this on your server. So there's an initiative called the WebAssembly System Interface, called WASM, and that's an interface that defines an ABI, application binary interface. So that specifies how actual data is being passed in and gets get returned, and an API. So how do you work with that interface? But that's designed to be portable to any platform, and it's very similar to POSIX. And POSIX is the standard for interfaces for Unix systems. and it provides things like file I/O, networking requests, etc. And one of the reasons why people are very keen on having this is because security has been part of its design. So you get sandboxing, but you also get capability-oriented code, which means that by default you can't do file I/O, you can't do open a socket. You have to explicitly ask for them, and this is basically whitelisting is instead of blacklisting, and that's a way better security feature than what most other runtimes offer you. It also has the potential, because of the well-defined ABI and API, and then pairing that with the fact that many languages can compile to WebAssembly, is that you could theoretically interface between any language that compiles to WebAssembly. So if you have language A that compiles to WebAssembly, language B that can compile to WebAssembly, then via WASI and its interface, you could exchange data. So this could be the glue to link many different languages to each other. And then finally, just to become a bit more hyperbolic, Solomon Hykes, who was one of the co-founders of Docker, he wrote in 2019 that if WASM plus WASI had existed in 2008, they wouldn't have needed to create Docker. So that was by one of the Docker co-founders. So you can see that many people are starting to recognize its potential as a game changer, basically.
It really is. Yeah, it's really interesting. I think it's going to be fascinating to see how it plays out. And I think once the different language support gets maturer for different languages, it's going to be really interesting to see if JavaScript holds on to that sort of elevated place that it's taken in the programming ecosystem, or if other languages start to take its crown a little bit. Be an interesting next decade as we see how the web evolves to it. That was all great. Thank you so much, Erik. If someone's trying to decide which of the languages to try out in Nibbly November, how would you help them decide?
So if you've never worked with an assembly language, it can be slightly daunting, but I would still recommend trying it. And then probably WebAssembly is the easiest language to get started with, partially because of the expression-based format is actually quite nice to write, but also because the stack-based model is, I think it's one of the easier to visualize and to start out with. But you could argue it's not a real assembly language because it compiles to bytecode. So if you want a assembly language that compiles directly to machine code, I would argue that MIPS assembly would probably be the best way to start because of its reduced instruction set. So it has a limited set of instructions that makes it a lot easier to get started. And one of the benefits is that the MIPS track on x86 uses a MIPS simulator. So you can run it on different platforms. You can run it on an ARM platform or on x86. It will just work as if it were a MIPS platform. So MIPS assembly, if you want to compile, if your first assembly language and you want to have it compiled to machine code, and otherwise maybe WebAssembly. And if you're working on an x86-64 machine and you want to know a little bit more of how that's actually working under the hood, go try out x86-64 assembly. So you might even recognize a couple of the errors that you've had. Well, for example, when working with a C or a C++, because they are also quite, they can be very tightly linked to x86-64, especially when you write inline assembly. But in general, it's just very good for you to understand how your CPU is actually running things. If you're familiar with Lisp, you appreciate that WebAssembly uses S expression, so maybe try out that. If you are working in the web space, or you're working on web apps, WebAssembly is the most logical option of these. And if you care about performance, you probably want to go with x86-64 or MIPS. Of course, if you care about web performance, you just try WebAssembly. But basically, you can't go wrong with performance because that's what assembly languages are partially for, to get us high performance.
No, indeed. Brilliant. Thank you so much, Erik. everyone, I recommend definitely trying out an assembly language this month. It's
Do
a
it.
fascinating and fun thing, and super, super satisfying when you get your code passing in assembly. Just as Erik messaged me on WhatsApp being like, oh, I just got this and it worked first time. It really is a feeling that's worth shouting about once you feel like you've solved a good exercise in assembly. So yeah, definitely give it a go. I'm going to be doing that for sure and playing around with it. I think I'm probably going to go with WebAssembly just because I've not done that before. I've done the others in the past. But yeah, super excited. That's it for this video. Do check out the new Community Solutions functionality as well. Got some more of that coming soon. Really excited about that. And I'll see you next month for our final video of 12 in 23. I can't believe how quickly the year has gone. But thanks so much, Erik. Thanks everyone for watching. I hope you have a great November.